thing now. Okay, and let me see, got it. And everyone should have a Bayesian inference engine. So I'm just going to start with a couple of quick slides. I wasn't going to because this is all workbook based, but actually these are some slides I gave from a talk about a year or two ago about Bayes. There's just 4 or 5 of them, and it's one of those I'm not quite sure how to. It's a big topic, and it's kind of like, here's statistics. So anyway, that's kind of where I'm going to say. So I guess first things, taking it from the top, you're all very welcome. It's great to be back in 2022, especially under somewhat cautiously more optimistic standards here in Ireland. For those of you who are Irish based, the government has essentially eased most of the COVID restrictions as of this weekend. And I wasn't in town, but my wife was, and it sounds like everyone almost immediately reverted to type. The pubs and restaurants were absolutely packed, apparently. So we'll see. I'm still a bit cautious about opening up, and I was just talking to someone before we began. We are hoping to, have in-person events again, and start for the first time basically in 2 years later in 2022. But it'll probably be March or April, to be honest, because it's a question of not just being able to do it, it's also getting enough people who are comfortable meeting in person and also having speakers and stuff. Although I imagine just in terms of getting the pipeline back up and running, the first in-person event will be given by either myself or Richie or Pedro. I say Richie or Pedro, I haven't actually asked them yet, but usually they're good. They've learned to not get too upset when I volunteer them for stuff. But anyway, one thing that definitely will happen in 2022 is the workshop series, and I think they will always stay virtual and online. We used to run them in person, basically above a pub in the Dublin city centre. But to be honest, I don't think they lose that much in the virtual setting, and it is much more convenient just because of the nature of it. So I think they're never going to change. I think that's kind of one of the effects of COVID, is that will always kind of do this. Now, for this series here, I kind of decide, it's a talk I always like, which is kind of an introduction to Bayes and Bayesian statistics and, Stan and all that good stuff that people have probably heard about. The one problem I've always had in teaching it, though, is like the examples are always a little bit contrived, and they, it's tossing coins and estimating probabilities of heads and all that kind of stuff. And I've always found that a little bit twee and unrealistic in many ways. I've never been entirely happy with it. And then last year, we kind of, for the workshop series in 2021, I ran basically a data science soup to nuts series, which was all about basically starting, running, and finishing a relatively I don't want to say straightforward, but a relatively short data science project, pretty much from soup to nuts, start to finish. And as part of that, it was on an online retail transactional data set. And one of the reasons I do these is because basically it's a way of me kind of getting stuff done. It kind of the intrinsic motivation for me to run these workshops is that it lets me either learn a new technique or thing I've been interested in, or kind of figure out what's, the more modern packages around it, especially with R, and how all that works. And one of the things I was going to that kind of motivated me for last year was to learn customer lifetime value models, which I hadn't really played with much, but I'd heard about because I had a couple of friends who had kind of used them in anger, and they were quite happy with them. Now, as it transpired, what happened was they just proved a bit beyond the scope of the workshop series last year. There was just too much going on, and it was kind of that classic case of I was trying to keep everything nice and contained, and even as it was, it kind of went to 8 workshops. Now, I probably could have got it down to maybe 6 with the benefit of hindsight, but there was still quite a bit of content in there, and it would have taken, I kind of realized pretty quickly that it was just going to take too long to cover the topic properly. So my idea was always to kind of run a workshop series in customer lifetime value, but also I discovered there was a couple of people online who had kind of implemented some of the basic customer lifetime models in using Stan and using Bayes in general. So I kind of thought, well, actually, even though customer lifetime value is a little bit of an advanced topic, it's certainly more complicated than it's a bit more sophisticated than people like think it is. It also occurred to me that this was a kind of a good real use case for Bayesian statistics. So rather than actually I'm kind of doing a hybrid approach. I have no idea how well this is going to work. This might prove to be kind of, two missized jigsaw pieces and trying to shoehorn them together. But I don't think so. I think we can do it all. We just might not cover an awful lot of customer lifetime value for a couple of sessions, or at least not directly. We're kind of going to ramp up to it. But the main thing I want to talk about is, Bayesian statistics first, and Bayesian, and that everything that we're going to do in this workshop is going to be effectively taken from that standpoint. So, and my idea is that even if you've, no idea about, Bayes before, or a bit of code or whatever, I'm going to try and make this as beginner friendly as possible. And each individual workshop will try to make as standalone as possible. Now, that's not entirely practical in real life, because I know one thing leads into another. But I do try to make it so that, it kind of happened, and it's been my experience that this has always happened. People just appear. One person appeared for the first time at the very last workshop of the soup to nuts one. He appeared in December, and he was actually very, he participated quite a bit throughout the workshop, but he'd missed all other 7. So I appreciate that's going to happen, but it's either that or just do a whole load of series of very unsatisfying 2-hour workshops where you try to cover a load of content, and I think a lot of people just get lost, or you just kind of do it this way, and this is kind of the way we've kind of evolved into. So like I said from earlier, if anyone has any questions, I'm keeping an eye on the chat. I generally don't miss them, but sometimes I do. If anyone has any questions or wants me to put wants me to cover something, or if I say something and it doesn't really make sense, or it prompts a question from you, by all means just put a question into the chat. I'm happy to address it. Like I said, if it's a big tangent, I might hold off until either after the talk or like the break. But I'm more than happy. I actually like getting feedback, because it means I'm not just talking to a blank screen and seeing a picture of myself, which gets a bit weird after a while. So please, by all means, if I say something that sounds like it's complete nonsense, please get me to explain it again. I'm more than happy to do that. So in terms of the structure of the overall workshop series, I'm not quite sure is the short answer to that. This is kind of a learning as we go, a bit like last year. And for those of you who have done any of my workshops before, you'll probably be familiar with that. And if you're not familiar with that and interested, there's a series of YouTube videos on our Dublin Data Science YouTube channel that kind of goes through it. It's basically me rambling for 2 hours and talking about maths and stats, and pontificating at length on various topics. And I don't know how long it'll be, and I'm not entirely sure how much we'll cover. We probably won't cover a huge amount of the really kind of sophisticated Bayes stuff. But I'm going to try and make it as practical as possible and as realistic as possible, which is like, especially with things like, a misspecified model and divergent transitions and stuff. I don't think we'll cover them tonight, because the models we'll be building, if we even get to them tonight, will be relatively straightforward. But it is a major topic, and it's usually the first hurdle that people fall over at, and like, what do you do next? So before we begin on that, though, I'm going to kind of deal with what Bayes is. I want to talk a bit about conditional probability, talk a bit about how things work and where we're coming from. But before I get into the workshop, like I said, I had a couple of slides about what a Bayesian inference engine is. Sorry, hold on, let me just move this down here. And basically, the Bayesian inference engine conceptually is actually very similar to how our brains work. And I think that's partly why I like the Bayesian approach so much. I mean, there's a couple of reasons I like it, but I think from a like a conceptual point of view, it's not just things in a vacuum. You have prior knowledge about something, which is represented by prior distributions. And then you have the data that you have observed. And then from that, you get posterior knowledge. Now, the great thing about the other thing that a lot of people don't talk about is this kind of comes from a somewhat related, but not necessarily exactly the same topic of generative models. So sometimes you can actually work on things without any data at all, which I know sounds a bit kind of blasphemous, but with generative models, if you're kind of building a simulation of how you think the world works, and even if you don't have that data part here, that's kind of in the middle. I don't know, if you guys can see my mouse? I don't know if you can. Oh, I think you can actually. The data part is it's not, I don't want to say it's optional, but it's not necessary is the way to phrase it. Now it's less than ideal. You would like to have some reasonable amount of data that you can base your inferences upon, but there are cases where that's just not possible. And then you can use some of these techniques to actually, to get somewhere. And I have heard people who have done that, and I've done that in the past, because essentially what you're doing is quantifying your prior knowledge. Now, you don't really have a posterior knowledge now because you don't have any data. But basically what Bayes does is it's a logical, mathematical, and consistent method for basically running this equation, combining your prior knowledge with your data to create a posterior knowledge. And it does that in essentially what is a logical way, as opposed to the way our brains do it, which is, essentially nowadays semi-random in advance, But that's basically how our brains work. We have beliefs about the world, then we have observations, and then depending on how strong our beliefs are, the output of observation changes our beliefs. Now, unfortunately, it's funny the way the world has changed. When I first started getting that, I would talk about, how really, really strong priors kind of ignore data. And, people didn't really get what I was talking about. But nowadays, with our polarized world and all the politics, almost data has become somewhat irrelevant, and no amount of data can change people's prior knowledge, with everything becoming so factionalized, certainly when it comes to politics and things like that, unfortunately. But, it's a similar idea. I mean, you can actually capture that. Now, we probably won't, maybe we will a little bit later, depending on how things go. You can actually see that mathematically. Basically, if you have very, very strong priors, it takes an unreasonable amount of data for your posterior to look different to your prior, is basically what that means. But anyway, that's kind of what we're looking at. And in the discrete variables, we're going to talk about this shortly. This is kind of like the classic Bayes theorem. If you look at Bayes theorem online or any of that kind of stuff, it's kind of telling you that. Now, in probability speak, what this vertical bar means is that B is conditioning A. So essentially, we have some knowledge B, and we want to assess the probability of A. And essentially, what we're saying is that the probability of A conditional on knowing B is the same as multiplying out the probability of knowing B conditional on A times the unconditional probability of A divided by the unconditional probability of B. So it's essentially the reason why, and I talk about this in the workbook, which I'll probably skip in a few minutes because I'm covering it here. What we're saying is it's also known as inverse probabilities. So given that we know something about A given B, what can we find out? Or sorry, the other way around. Given that we know something about B given A, how do we invert that to say, oh, now we know something about A given B? And that is actually a very, very practical thing. It sounds a little bit kind of esoteric and, fancy maths, but actually it's not. When you actually break it down, it's actually how the world works. And in the continuous case, rather than A and B, this is kind of the discrete variables. This kind of works. For continuous variables, we generally change our labeling a little bit. We have parameters of our continuous parameters, theta, that we want to do inference on. And this is basically most statistics. So we have some unknown quantities that we want to do inference on. And then we have some observed data, which we represent by D. And then essentially, we have some prior beliefs on these parameters. We kind of roughly know what, we have some idea what these parameters are going to be, generally around, you rescale your problem to be around unity. So that, there is single digit numbers are the units that we're dealing with. Then we have a likelihood model, which is, given a particular set of values of theta and given some observed values of D, how do we calculate that? And then we have a posterior, which is the opposite of the likelihood, which is given the data we've observed, which is D, what does that tell us about our inference? And you'll see basically that, you know, the posterior distribution is a combination of the prior and the likelihood. And in the continuous world, it basically becomes integration. So we're dealing with high dimensional integrals because, you know, what's the difference between a likelihood and a probability? That's an excellent question. So a likelihood is not a probability. So there's a couple of technical explanations which I'm not going to explain because, to be honest with you, I always get it confused myself. But the way to think of a likelihood is the likelihood is the output of the density function. So a likelihood is not constrained to be between 0 and 1, right? A likelihood is a density. Like if you think of it in terms of the continuous world, basically the likelihood is, if you think of a density function, right? That density, it's only the area under the curve that has to be 1. But if you have a range of values that are less than 1, or, you know, it's compressed around a very narrow set of values, that likelihood value could be much greater than 1 or much less than 1. So that's kind of the difference between the two. So the likelihood is the output that you get from the density function. Is kind of, so if you go onto Google and you get like the density function of a Gaussian or a Poisson or whatever, the likelihood is the output of that function. Does that make sense? Yeah, okay. And that it's easy to get them confused because English tends to use them very interchangeably. So we often say, you know, what's the likelihood of something happen? We're basically talking about a probability. But in statistics, the likelihood and a probability are they're distinct but related concepts, and it's easy to get them confused. So that's kind of the simplest explanation from it, how to think about it, okay? Whereas a probability is a very constrained parameter. A probability can only ever have a value between 0 and 1. The total value, you know, across the entire universe of outcomes, the probability of something is 1. And if something is impossible, it's, you know, it follows all the usual things that we know about with the probability. But a likelihood is just kind of a mathematical function that you use to calculate probabilities. Okay. So hopefully that makes sense. Now, I appreciate that's a very hand-waving answer. And I'm trying to kind of give intuitive explanations. If there's any like professors of statistics here who want to get more technical, by all means, please do. Share it in the chat or put it in, like we can talk at the break. But that's basically how it works. And essentially, your likelihood model is essentially your model of how you think the world works in terms of the data that you're observing. So you have your prior distributions, which are your prior models, but generally it's your likelihood that's the most important part in terms of determining your model. So it's like, am I going to use a Poisson to explain this data, or is it a Gaussian distribution, or is it a gamma, or is it log normal? All those kind of things. Those tend to be kind of your likelihood to how this works. And like I said, it's a high dimensional integral because if we have, you know, lots of different, if that theta could be, say, for example, if we have a regression model and we have a couple of categorical variables, you know, then you have k-1 parameters for each of those, where k is the cardinality of the categorical variable. So you could easily have, you know, it's very easy to create a regression model with 25 dimensions or 30 dimensions or 100 dimensions. And from practical point of view, calculating those high dimensional integrals in kind of using the brute force approach is essentially impossible. You can't do it. So that's why we need specialist tools like Stan and a few other things with Markov chain Monte Carlo to essentially estimate these intervals or bypass them, for want of a better word, but still give us, you know, robust statistical answers. Okay. Or I should mention, basically, I'm not going to talk for 2 hours straight. Sorry, I just keep getting, I should have notes here to say the order. We are going to take a break sometime around the hour. So in about half an hour, we will take like a 5 or 10 minute break, let people run to the loo or grab a cup of tea or whatever. I'll also use that opportunity to answer any kind of technical questions or if people want to hang around for like before we start back. So this won't be just me talking solidly for 2 hours. So if there is any questions more about any of that I've just talked about, we can address them there. So yeah, we use MCMC. So you'll hear people talk about MCMC. It stands for Markov chain Monte Carlo. So it's a way of basically estimating these high dimensional probability distributions. And rather than calculate probabilities directly and come up with like analytic functions, essentially what we do is we sample all the parameters from this posterior distribution using, Markov chain Monte Carlo, which is essentially a well-known statistical technique at this point. And what we do is we collect a number of samples from that distribution, and we use that sample to do all our inferences, because that posterior is an estimate of our posterior distribution, because we can't really calculate it numerically or analytically or anything like that, because integration is hard to do, and it becomes very, very difficult to do at very high dimensions, because essentially the curse of dimensionality kicks in. So that's why we kind of need tools like Stan, or there's a few others that work it. I definitely prefer Stan, but there is machine learning work being done in things like TensorFlow probability and Torch. I think PyTorch does some of that, has some kind of approximate Bayesian stuff. For various reasons, I'm not a huge fan of them, but I see their uses, but they're not much work to me in practical just because of the things I work in. But we can, again, that's a conversation for probably a little bit later down the line. But that's basically where we're coming from. Oh, sorry, PyMC, yes, sorry, good point. Well, PyMC is essentially the same, Nathaniel. It uses the same underlying technology as Stan. Yeah, and PyMC is the one I always forget. And I think there's a PyMC 4 now. Is there, or is it still PyMC 3? I think there's a PyMC 4. Yeah, and it uses what's called Hamiltonian Monte Carlo, which I will talk about a little bit later, but I won't go into too much detail. That's it, still 3, but 4 is on the way. Yeah, I actually had a talk from Chris, what's his name, the head guy from PyMC. He's great. I can't remember what he started out. Basically, it was kind of a pet. Chris Fonsbeck. Thank you. Yeah. And if you're interested in any of that, so now most of this, I should say, at the nailing my colors to the mast, I'm pretty much an R guy and a Stan guy, but the vast majority of what I'm covering will be very readily translatable, I think, into Python if you're using PyStan or Command Stan Py, because the Stan code will be exactly the same. And I think I'm not using anything particularly fancy in R. I'm using a few of the packages that have been built around Stan, but I think Arviz and Command Stan Py has a bunch of that in it. And I think the translation to PyMC3 is reasonably direct, but I'm not quite sure. I'm not an expert on PyMC3. And the kind of the Python community, I think, is kind of split, although most people use PyMC3. But I think there is a growing group of Pythonistas that use Stan now. But I'm not aware really of. I think the capabilities are broadly in line with one another. And I think there's an awful lot of yeah, okay, excellent. Thank you, Nathan. Yeah, it's pretty, from what I remember of looking at the model blocks, like the model block and setting up your priors, it was fairly straightforward, but it's written in Python as opposed to written in a separate language like Stan does. But I'm getting a little bit ahead of myself. I'll talk about that. But what I'm saying is that a lot of this stuff is very, very usable now. However, and this is kind of one of the reasons why I want to, and it's worth having a proper like series of workshops on this, is the problem with Stan and PyStan and these HMC models is, and the Bayesian models, is that there's two major, there's one definitely major drawback, which is kind of unavoidable, which is it's computationally a lot more expensive to do, because rather than getting single point estimates of your values, you're sampling from a posterior distribution. So if you think of it, rather than getting one set of values, you're getting 2,000, 3,000. So you're already talking about, just inherently in your head, it makes sense that, you know, you're dealing with orders of magnitude more computation required, even to like fit fairly simple models. And the other one is sometimes it breaks. Now, the reason why Stan breaks is because, and HMC in general breaks, is it identifies problems with what you're trying to do. Whereas other models, because they're estimating point estimates, so it's very easy to write bad models, even in general. And the problem with things like maximum likelihood maximum likelihood models and all those kind of approaches, when you're trying to get a single point estimate, you can kind of ignore a lot of problems with your model, and they often manifest in all sorts of different ways. And STAN and PyMC3 and HMC in general, because you're trying to explore a surface for your posterior distribution, they throw those problems, they kind of identify those problems and they throw out errors. Now, initially that's incredibly frustrating because you're just trying to get stuff done. But what it's telling you is that you've set up an invalid model somehow. Either the model you're trying to set up doesn't really agree with the data, or you need to change something, or you've actually coded something wrong. There's all sorts of different things that could be going on. And it's a feature, not a bug, that HMC complains loudly when you do that, because it means essentially, and these are real issues, it means that your statistical inference is wrong, or at least could be wrong, and you've no way of knowing. So from a precautionary point of view, you can't accept the values you're getting. Now, in some cases, it doesn't make a difference, but there are quite a lot of examples, canonical examples, that we'll probably talk about later, where you basically get the wrong answers. And what happened was there was an old piece of there is a piece of code that still gets used a bit called JAGS that was kind of inspired STAN, and it used a different underlying technology called Gibbs sampling. And people didn't notice there was a problem with it until they ran their Gibbs sampler. I think essentially Andrew Gelman, who's one kind of the statistical kind of leaders of this project of STAN. He's not entirely a leader, but he's one of the philosophical guys behind it all. I think he left something running over the weekend, and when he came back, he noticed there was problems that had never been identified before because no one had left a sampler to run as long as it had. And essentially what happens is that a lot of statistics is based on asymptotic behavior. So essentially, if your sample size goes to infinity, then things work out. The problem is, in the real world, we don't have the luxury of dealing with asymptotic data. We have finite data sets. We don't have infinite data sets. So things that work in the infinite data world can give you very bad answers in the finite data world. And essentially, that's what a lot of this stuff boils down to, is that, and I mean, it's totally understandable. It's back in the day, we didn't have strong computers, so computation was incredibly expensive. And the only real way to deal with these problems was to do the maths. And the only way to get the maths work was to take limits to infinity, and say, okay, well then asymptotically these things work, so these are the techniques we're going to use. The problem is that when you go from an infinite world to a finite world, you've now got a new set of problems that you didn't necessarily have before. So a good example is, if you can imagine an infinite sequence that goes from 0 to 1 to 0 to -1, so, and jagged like that, on average the value is 0, but you're not going to get it to 0 with a finite sample, because depends on where you are. Or let's say it goes to 100, and then it goes to 0 for 100 data points, and then it goes to -1 for 100 data points, goes back to 0, then and so it's very easy to just create relatively contrived toy examples that to show where, when you go from the infinite world to the finite world, you can have problems with your inferences. And that's basically what STAN tries to deal with. We kind of put a bunch of limits around what we want, and if we don't observe them, while we can't be certain we're correct, at least we know there isn't definitely a problem. And you can, there's a bunch of stress tests you can do to try and look for these problematic areas, but we're kind of getting ahead of ourselves. But I'm trying to create the motivation, and these manifest themselves very loudly, very, very annoyingly. They're called divergent transitions. It's a very, very common question on, I think, the PyMC forums, and definitely on the STAN forums too. I'm getting all these divergent transitions. Can I ignore them? The answer is no, you can't. But we will deal with that a little bit later down the line. Okay. Does anyone have any questions? How's data table for the? So I haven't used data table in a long time. It's a very R specific question, Des. As far as I'm aware, data table and pandas are roughly equivalent in terms of computational, but I'm a bit out of the loop in that. I kind of switched over to the tidyverse in the R world about 2015, 2016, and I've never really looked back, because the problem I found with data table was my code ended up being like hieroglyphics, because it was very hard to decode. It was very, very fast, and I would probably use it. Was it ported to Python? Oh, okay. Oh, wow. And was it done by the guy, not Wes McKinney, he was the Pandas guy, the Matt Dowell. Did Matt Dowell actually port Python? Was Matt Dowell involved, or was it a bunch of other people? Yeah, and the other thing is, I think it's also the classic kind of engineering thing, in that I think the data table guys don't really get on with the Pandas guys or the other people. So there's all that usual kind of drama and politics. So I kind of didn't pay attention to it. So I know there was definitely a bit of kind of engineering one-upmanship going on, whereas to my knowledge, Wes McKinney and Hadley Wickham, who does the tidyverse stuff, they actually get on quite well personally, and they interoperate a lot and stuff like that. So it's pretty good, Des. I probably wouldn't bother with it unless I needed it. And I haven't really needed it yet. Now, there is actually, I'm working on something on the side that might require it, but that's more of a memory issue, I think, than data table. We'll see. Maybe give me a shout at the break or after this, Des, and we can have a chat about it. All right. So, okay. So that's basically where we started. I'm now going to go on to our kind of the workshop properly. And we're going to start, I'm not really going to start in the Bayesian world, even though we are going to do Bayes rule, because the weird thing about Bayes rule and Bayesian, and sometimes there's a bunch of things in the machine learning and statistic world that have the word Bayes in them, but they're not Bayesian in the more traditional definition of what being Bayesian means. And being Bayesian means you're dealing with posterior distributions, you're thinking in a Bayesian way rather than a frequentist way. And it's the whole, again, talking about culture wars, it's the whole Bayesian versus frequentist nonsense. They both have their places. I tend to think in a Bayesian way, but you know, there's a lot of really good frequentist stuff that's very, very useful too. And Bayes rule isn't necessarily Bayesian, because you know, it's basically a cornerstone of statistics, and there's an awful lot of Bayes stuff in Bayes rule in frequentist statistics too. So I'm going to start with just some very basic statistical concepts that isn't necessarily Bayesian. We'll kind of get to the Bayesian stuff later, but to kind of understand it, I've always found it useful to talk about conditional probability, how Bayes rule works, what it does, and what we're doing, and then kind of build on that to start talking about, you know, the Bayesian concepts. Okay. So we've got, I mean, I'm going to go with the very basic question of, you know, we have two binary variables, A and B, and they're related, but they're not actually the same thing. So they're not necessarily independent, but they're not essentially giving you the same thing. They're not fully deterministic with one another either. So, I mean, the way I always did it, and at the risk of becoming, you know, getting myself into trouble, but I'm going to, you know, I can't help it. Like a moth, I'm drawn to the flame. We're going to assume this is a medical test. And I'm using some of the word, like, because when again, the way the world has changed, when I first started talking about this, this is all very hypothetical. Now with COVID, everyone is very, very familiar with these ideas. Now, the other thing I should say is this is not in any way talking about actual COVID tests in the real world. I'm just using medical tests like COVID for the purposes of describing this. Now, I do mention the COVID tests here, and I'm using some of the numbers that they got for reference, but these aren't actually saying what I'm saying. I've got that backwards. I'm not saying anything about COVID. So what I don't want to do is get flamed by a whole bunch of people saying I'm a COVID denier, because I'm not. I'm all jabbed up. But I also don't want a whole bunch of people who are, you know, anti-vaxxers thinking I'm a tool of the deep state or something either. So I appreciate that maybe I should have chosen something else. But also, this is the one I always done. And basically, I'm not going to let that kind of, I mean, you know, we're talking about statistics here, because there's a whole lot of other stuff going on in the real world, and this is just a model. in the real world, actually running medical tests has way more stuff going on to, to counteract these things. But the reason why I think it's useful doing it is it's important to highlight just how difficult this stuff is and how impressive the whole medical establishment is at just dealing with the basic facts of probability that are actually quite hard to deal with. So, especially when it comes to like low base rates and stuff, although we don't really have the low base rate problem anymore when it comes to COVID, certainly not in Ireland. I don't know what the estimates are, but the prevalence in the population is considered to be quite high now. Okay, anyway. All right, let my career suicide commence. So we have two binary variables, which are a true and a false. Okay, so we have two values A and B, and they can take two values. So let's say, for example, one is A is whether or not a person is infected with COVID, or any other medical virus, or any other medical test that we're testing for, and B is the result of a test that the person took trying to detect that medical condition. Okay, now you might think they're the same thing, but they're not, right? So one is whether or not a person has like some actual, whatever the biological markers are of actually being infected. So it's in your cells or whatever. And then the other one is the result of the test, and they're not the same thing, because just because someone tests positive doesn't mean they have the condition, and vice versa. So that's why you get into the whole true positive, true negative, false positive, false negative. So you have those combination of values, and they're not all one in one. A true result in a test doesn't mean you actually have the virus, in the same way that a negative result doesn't mean you don't have the virus, and vice versa. Now, you might do, but you also might not do. And we're just going to use Bayes' rule to just calculate some statistics on that. Okay? So, like I said, A is the variable looking for the presence of viral infection. So if it's true, then you are infected. And B is the variable result, is the result of the variable, is the result of the test that we took, right? So that's true or false. So basically, no test is perfect. So sometimes you can get a negative test, but actually be infected, or have, this could be a cancer treatment, whatever it is, right? Or you could test positive and not actually be infected, right? And ideally what we would want is for those negative, like those false results to be as low as possible. However, from a practical point of view, in terms of the real world, that's usually not really practical, either from an expense point of view or from literally, you kind of get not just diminishing returns. Sometimes it's diminishing returns, but sometimes, reducing the true negative rate increases the false positive rate. Or sorry, the other way around. That, like, getting a false negative, okay, we'll get that as low as possible, but we can't, there's whatever the chemical interactions that are happening, we can't help, but we're now going to get more false positives. So as a result, it's quite often a trade-off between one and the other. And okay, we could, and if you think about it, like a very simple way of doing that is, let's say fraud, right? In fraud detection, there is, you can get a really, really, really accurate result in fraud by just saying something isn't fraud, right? Because 99, I can't remember the exact statistics, but like going through Visa and MasterCard, it's something like 99.99% of transactions are valid transactions. There's only that, 1% of a percent of transactions are fraudulent. So you can get an extremely accurate result by just saying negative all the time. But if we want to get more positive tests from our test result, if we actually want to detect fraud, we can just be a lot less stringent in what we identify as fraud. The problem is that the more tests we give the more things we identify as being a problem, the more negative false positives we're also going to get. So they kind of counteract, and there's no real, generally in the, like, it's one of those classic in logic and in the abstract world where things can go off to an infinity, we can do this, but in the real world, it's just not really possible. So all these things become a trade-off. So basically what we're going to talk about is is how that works and how we do those calculations. It's actually relatively straightforward. Yeah, sorry, thank you, Stephen. Yeah, another common use case, sonar detecting a submarine from World War II. You had the exact same problem with sensitivity. And of course, the problem is that it's a pointless thing to just say no all the time, right? Even if it's a very, very, you end up with, super accurate. The problem is it's those false negatives that you really care about, because suddenly a U-boat appears and blows your shit up, right? So that's why, you've got that problem. But if we're more sensitive, you become the boy who cried wolf. And that is a big, big problem with a lot of fraud detection, because you have this low base rate, and it's something we're actually going to see in a little while. That the lower the base rate, it's also referred to as the base rate fallacy. The more rare something is in the underlying population, the much more likely it is that any true result from your test is going to give you a false positive. And that's just borne out by the statistics. There's no real way around that. So the only way you can do that is start driving your numbers down and down, particularly on the false negatives. See, what you want to do is get your false negatives way down. But again, in the real world, the interactions are the same, and you often can't do that. Okay? All right. Yeah, exactly. Yeah, there's other people's house alarms. Yeah, that's another great example. How often do you hear car alarms go off, or house alarms, or whatever? And it's basically a cat has been walking in front of the house. The problem is that sometimes it is a burglar, and your house gets cleaned out. But what are you going to do? So we have this. So basically, we denote this as the probability of A given B equal to small b, which is the probability of A given that we know the value of B is B. Now, we can also make that more general. We don't have to necessarily have full knowledge of B's value. If we have a probability distribution for B, that will make changes in the probability of A, and we can deal with that too. So we don't necessarily have to work with fully discrete cases, although to start with we will, right? But that's the other power, and that's where Bayes' rule comes in then, and where integration comes in, because we're not dealing with discrete values anymore. So those sums, things that were sums in the discrete world, now become integrals in the continuous world, and you've got the problem of doing all those integrals and stuff like that. Okay, so essentially what we're doing is, and this is where Bayes' rule came in, and I prove it out. I do a little bit of proof there because it's not particularly complicated. But basically, we have the probability of A given B is proportional to the probability of B given A. And the proportionality is this ratio of the unconditional probability of observing A times the unconditional probability of observing B. And a little bit later, and that's all Bayes' rule is. And Bayes' rule essentially just boils down to that calculation. And the problem is, in the continuous world, we now have to do integrals. But in the discrete world, unless we have massive cardinality where you're dealing with thousands of levels where it just becomes a pain, we can often solve these. And in this case, for binary, we can actually solve it analytically, and we're going to do that in a couple of minutes. But that's basically where we're at and what we're going to do. Now, I'm conscious of the time. So I think what I'm going to do is take a break here, because it's 7:45, and rather than go on, because we've got the new topic. So I'll basically explain what we're going to do after the break. So what we're going to do is we're going to take some input data. So basically our prior input values for false positives, false negatives, and the underlying prevalence. Those are the three numbers we need. And then we're going to run some simulations. And then we're going to show essentially Bayes' rule in action via simulation. And then once we've done that, and we're not really trying to put the world to rights. All we're trying to do is just get a feel for how the statistics of all this works, just going off the input numbers we have. Then we're going to basically show that while we can do it with simulation, in this case, we can also solve it analytically. And we're just going to show as well the effect of the various input values have on this, what we're calling a posterior probability. So given that we have some input priors, and given that we have a very simple likelihood model, which is essentially what we're doing here, how do those values change our inferences, and how do we work on that? Okay, so that's where we're going to leave it. It's 10 to 8 now. I'm actually going to stop here, and we will come back at 8 o'clock. I'm going to hang around for a minute or two. I will run off for a minute, but I'll give it a little bit. If anyone has any questions or if there's anything you want me to address, now's the time to do it. But failing that, we're going to take a 10-minute break, and we'll be back at 8 o'clock. No problem, Marion. Nice to see you again. But yeah, if anyone has any questions for the chat, I'll hold on for another minute or two before I put myself on mute and run off briefly. And then I'll come back, probably, it'll only take me a minute or two. And then I can address any other questions people have as well. Oh, hi, Grania, how are you? Sorry, I meant to start with that. Sorry, this is why. Yes, there is a GitHub repo. There it is there. Now, it's in the CLV workshop branch, Christoph. Yeah, everything I do, and I have a make file and a Docker file. So all of this runs in a Docker container. So it all becomes self-contained. One thing I did learn from last year is that I tend to change the Docker container as the workshop progresses, as time passes, and I either add new packages or the underlying containers get updated. So I'm actually going to tag each workshop, or at least every time it changes for a workshop. So I'm actually going to have different tagged repos as well. But everything is in the make file. So you just go make, Docker build image. I have pushed it up onto Docker Hub as well. I'm actually going to, that's one of the things, I gave a talk on this about 2 years ago about, it took me a while to figure out how I was going to combine kind of dev technology with kind of reproducible research. So I kind of have a way that works for me that I think we did give a talk on it, but the talk got lost. So I might actually give that at some point this year. But yeah, it's all fully available. There's even a code in there. There's extra code that we won't talk about. Like I generated some data rather than use the real data, just so that we would know the input values. And there's a couple of other bits and pieces, but we'll probably address them in a future workshop. Okay, well, what I'm going to do is I'm going to put myself on mute now, and I'm going to stop my video for 2 or 3 minutes. If anyone has any questions while I'm gone, please pop them into the chat. And then when I come back again, I'll give myself a couple of minutes to answer any of them, and then we'll start back at 8 o'clock. All right, I'm back. But yeah, thank you for that, Christoph. I actually meant to say at the start, I always, pretty much all this stuff I just put up on onto GitHub so that people can run it later. And in the last few years, I've started putting everything inside the Docker container too, so that it could essentially work by itself. I do a bit of weird stuff. I do a little bit. I do like some volume mapping and stuff, so that I wasn't entirely tied inside. So I can kind of work on my host machine, and then basically put the box around the code to run inside that. So that's why RStudio server. I tend to use the RStudio server rocker image for all this work. It works pretty well. I'm actually pretty happy with kind of the workflow and stuff. It's you kind of get the benefit. And ironically, because Des, you were asking about data table. It was actually data table kept breaking on me. So I went back to use some code I had written a couple of years ago. I went back to reuse some code and it had all broken because data table had upgraded, because all the API had changed. So that was the point at which I realized for these things to actually be properly reproducible, I was going to need to be able to run them inside a Docker. But it worked pretty well. I just kind of rolled back in time, created a Docker image around the time that the code had been last updated, ran it inside the container, and it worked perfectly. Be curious to hear what you think are the main benefits to generative modeling over. So with generative modeling, you actually don't really need any data. That's the big one, I think. And sometimes you just don't. I know that sounds like a ludicrous statement, but I work in finance and in insurance primarily. And sometimes you just don't have any data, or the data you do have is highly, highly aggregated, and you don't have enough of it to really run your proper machine learning models on it. To be like, I've seen data sets where you have like 100 or 200 data points, and it's aggregated, and the data isn't the real data because you've got to project forward your claims in time. And I do know someone who basically built a pricing model in insurance based on no data whatsoever, because it was a really specialized business that they didn't really have anything typical for. So he just took some of that. He just basically used his prior knowledge. He kind of used it against them. Basically, they were like, it's absolutely impossible to do any of this because the data doesn't work and blah blah blah. So he did the classic thing of, the way to get information out of people like that is to tell them something that's wrong, because people love to tell you when you're wrong. So what he did was he went off and kind of, using some very simple assumptions, he built a pricing model based on some very simple inputs, and then got told how he was wrong, and then wrote down all the different ways in which he was wrong. And that helped him kind of improve the model. So now it's entirely possible. I'm a little bit behind on machine learning. I haven't really looked at it. So that's the other thing. I mean, generative modeling isn't necessarily different to machine learning, because you can certainly use generative modeling as part of your machine learning, certainly to calibrate it and to check what you're doing. And sometimes it's very useful to do that. So build a system, and we're actually going to do that, probably not tonight, but essentially build a system, generate some data using, set some values for your model, create some synthetic data, fit your machine learning model on the synthetic data, and see, can it recover, either A, recover the parameters, or B, can it make how good at predictions, because you know what the true underlying values are. So that would be generative modeling as well. Bayesian statistics is a bit different, because typically with machine learning, the focus isn't on the underlying process. In many ways, machine learning is kind of designed that your underlying algorithms are essentially plug and play, and they're kind of built with APIs in mind, where the outputs just produce a prediction, and then it's all based on cross-validation and things like that. Whereas with this is a more kind of statistics approach, where rather than trying to produce predictions, you also, you care about your inferential model, but also you're also producing probability distribution outputs. That's where Bayes really shines. So rather than creating point estimates, you're creating a probability distribution of estimates, and that can be very, very useful as part of the decision-making process and stuff like that, because you're also capturing the uncertainty in your predictions as well as the predictions themselves. Now, there is there has been a lot of work in trying to blend the two. I'm not quite up to speed on where the cutting edge of that is, although one of the issues I think they found is that the computational requirements of going the Bayesian approach is sometimes at odds with the very large data sets you have in the machine learning world. However, the things they've had to do to get that to work break some of the guarantees and the usefulness of things like HMC. It gets a bit technical, and it's a question of horses for courses, and ultimately what it generally boils down to is, what is the cost of failure? So if the cost of getting your predictions wrong is relatively low, like for example, your marketing campaign, it means you just end up misspending your marketing campaign, and while that's not great, it doesn't kill your company. Whereas, in insurance or in, weather prediction or all the things, if the cost of getting your model totally wrong can kill your business or can, mean a whole load of people die, or like medical diagnoses, then your uncertainty is actually quite important to capture properly there. So it's, I have a preference, but it's also due to my particular use cases. I know a couple of, people whose opinions I really respect and admire, who would argue till the cows come home that I'm totally wrong in that, because they come at it from a completely different perspective. So, it's that in on itself is, I'm conscious that I didn't really answer your question. I know that, but the way I always look at it, it's useful to have multiple arrows in your quiver. So I think having some knowledge, I mean, we will be talking about this kind of stuff throughout the workshop. It's kind of, and it's also, it becomes a philosophical thing as well. So it's a question of what you care about. And typically, people just care, in most applications of machine learning, the only thing that people really care about is predictive accuracy rather than uncertainty quantification. And Bayesian statistics is particularly much more about quantifying uncertainty than it is about predictive accuracy, if that makes sense. And that would be, and again, in many cases, there is no objective truth here. It's a question of where your application lies and what the things you are that you value, what's the most important thing to you. Because generally, you are sacrificing one for the other as well. Going back to the no free lunch thing, if you care a lot about predictive accuracy, but not so much about quantifying the uncertainty, you can probably get, on average, much better predictions. But if what you care about is also the uncertainty of any given prediction, well, then you sometimes have to give up predictive accuracy to be able to properly quantify that uncertainty. All right. Okay, so we're back now. And yeah, like I said, that's the workshop there. Let me just sign in. We probably won't need me to run any code live. And, I always ignore all warnings to avoid doing that, as those of you who are familiar with my workshops will know. But you know what? I will just run it here anyway, just in case we need it. Yeah. No, it's up there, so I don't know if we'll get that far. All right, so the other thing I'm not going to do too much here is, because I am trying to keep it relatively general, is I'm not going to, I mean, I've done this code in R. I haven't done anything crazy with the tidyverse to do this. So while my pandas knowledge is a little bit old and out of date now, in the sense that I haven't really used Python in anger in about 3 or 4 or 5 years now. From what I remember, a lot of this stuff should translate pretty quickly. But basically what we're going to do is we're generating a whole bunch of patients, and we're essentially using the underlying prevalence in the population. So let's assume that we have 1% of the population with no further information. About 1 in 100 people have the virus, right? And I said COVID-19. The more I think about it, that was a terrible idea. Let's just call it the virus, and because it could be anything, right? And or fraud or whatever it is, the thing we care about. It's about in about 1% of the cases. Now, just to say, in how do I phrase this? In many cases, 1% is actually considered very, very frequent. In a lot, like in fraud, like I said, it's actually a lot lower than that. In most medical tests, it's a lot lower than that. In most, simply because most people in the vast majority of people in a given population do not have an underlying condition. So when you're doing these kind of tests, this is your problem. And also you have some tests, and you know that from the underlying statistics that about 5% of the time a positive test is a false positive. No, get rid of no, it's Data Workshops. Sorry, Stephen. Data Workshops is the name of the repo. That's WSCLV Bayes is just a folder within inside that. So if you just get rid of that last bit, Data Workshops is the name of the repo. Okay, so we have 5% false positive rate and a 5% false negative rate. So what that means is that given a positive test, right, we know that 5% of them are negative, are a false negative, and given a negative test, about 5% of them are false. Okay, but that's not what we care about. What we care about is what's the probability of having the virus given that we've tested positive, right? Whereas what those statistics are saying is the other way around. They're saying that given that I'm positive, given that I have the virus, I will give an incorrect value 5% of the time. Or given that I don't have the virus, I will give a 5% the time. But it's the opposite thing. They're assuming correct knowledge of whether or not you're infected. Okay? Whereas we want to know the other way around. We want to know that given that we have a positive test, and I realize I said this backwards at the start, and this is why I always cover conditional probability, because it's really confusing and it's very easy to get yourself confused by this. In fact, one of the things I always joke about, and it's not really a joke, I mean, it's funny, but it's also the truth, is that whenever anyone asks me a question about conditional probability, I immediately go with my intuitive answer and then say the other thing, because it's almost always the opposite of the way my intuition. Intuition is not your friend in the world of conditional probability. You kind of have to stop and think about it and do some calculations in your head. Sometimes you can do them in your head, and sometimes you have to get the pen and paper and the calculator out, right? So, sorry, let me start again. So, when we say these tests have a 5% false positive and false negative, we mean that if someone is infected with the virus, then we get a false negative 5% of the time, as in the test is negative, but it's not really a negative. The person is actually infected. Okay, so that's correct knowledge of B. Whereas the other one is the false positive. So let's say the person is not infected, then we get a positive result 5% of the time. Okay, so we have some probabilities based on knowledge of the person being infected or not being infected. But we don't actually know that in advance. We want to know the other way around. We want to know, given the results of a positive test, what does that tell us about whether or not the patient is infected? So we're looking to do it the other way around. So we have knowledge. So we basically have we can give probability statistics based on correct knowledge of whether or not the person is infected. But what we want to know is the other way around. We have correct knowledge of the tests, and we want to know what that infers about whether or not the person is infected. Okay. All right. So how does that work? So basically, what we do is we have 10 million. That you're in the Stephen, you are in the master. You need to change into the CLB workshop branch, because I haven't merged it into master yet. And if you have issues during it, I'll just get it at the end. I'll sort you out at the end. So all right. So how we do the simulation is I'm not going to really go into the code. The code basically does what I'm describing. We essentially generate 10 million simulations, so essentially 10 million people or patients or whatever. We randomly give them, we say, are they infected or not? And 1 in 100 is infected. So let's say for example, it's roughly 110 million, then about 100,000 people on average within the data set will be labeled as true under infected. Okay. So we do that. Then we now have kind of two subsets for the data. We have infected and non-infected, right? Based on whether or not the infected variable is true or false. If the person is true, we then allocate, as in they're infected, we allocate a true result 95% of the time for the test result, and a false 5% of the time, because that's the false negative. Okay. And then for the uninfected people, we do the same. We have a 5% false positive rate. So for the uninfected people, we give them a true test result 5% of the time, and 95% of the time we give them a false one. Okay. And then we run that simulation. And then so in the end, we have basically three columns. We have like a patient ID number, which is just a number. We have an infected logical, which is true or false based on whether or not they're infected. And then we have a test result, which is the results of our test. Okay. Is everyone kind of following that? So essentially we've had to, because the test behaves differently depending on whether or not a person is infected, we have to do the simulations in two different ways. And those numbers are essentially, for the purposes of mathematics, those two numbers are separate from one another. We can move the false positive rate up and down independently of the false negative. And that's something we're actually going to do in a couple of minutes. We're going to vary all those around and see what effect it has on the output. Okay. Stephen, I've seen your question, but rather than take it, I'll deal with it after we're done. Once we're done with it, okay? I'll step you through that. Okay. Right. So now we have a whole load of proportions. Okay. So how do we actually get like an empirical estimate of the conditional probability? Well, what we want to do is we want to subset on all the people who tested positive. And then we want to find out what proportion of those people who tested positive are actually infected. So essentially, it's just a summary query. Like we're just going to we're going to filter on all the positive tests, and then we're going to get the proportion of people who are actually infected and not. And that will give us an estimate of what the posterior probability of the person is. So in advance, if you think about it as the prior probability is 1% of the population. And then afterwards, given conditioning on a test, we now have a posterior probability on that person. Now, what we want that probability to be is a true test. We want it to be highly likely that the person is actually infected. Okay. But actually, if you look at the numbers there, and let me just zoom in here a bit. Let me just move that up so people can see that a bit better. The key number we're looking at is actually this one here. Right. So you can see that a true positive is only about 16% true. And that's actually relatively good. Like that number is relatively high, as in there's a 1 in 6 chance that it's a true result, because the prevalence is relatively high in the population. As the prevalence drops, that number gets much, much worse. Right. And now I know that's always a surprising result. The only people I have found who don't find this surprising are people who have done this in like some kind of elementary statistics class, because you're aware of this issue, because intuitively people don't get this right. And back in it's become a lot more popular as machine learning and statistics has gotten more popular from people doing courses and stuff like that, because this is the kind of thing that's done as an exercise. But back in the day, like when I first started teaching this course, almost no one would get it right. As I've started doing it, and I do mention it from time to time, if I'm just doing like straw polls in classes, or if workshops that I'm running or talks I'm giving or whatever, the number of people getting this right has gone up. But generally when I've asked them, it's because people have like seen it before and they're aware of it. Sorry, I'm talking a lot, so I'll just lubricate the voice. So what's going on there? Well, when you think about it, the problem there is when you've got a very low base rate for something, your false positives, the problem is that essentially when you have a large number of people who do not have the test, right? They don't have the underlying condition that you care about. In this case, 99% of the population. Then your false positives are going to be way, way higher than your true positives. Simply because if you think of it as two feeders, so at the start we have the whole population. We're splitting them into two buckets based on 1% of the population is tested, is infected, and 99% of it isn't, right? And then even though we have a very accurate, so we're not losing very many people from here, right? Because there's basically 100 times more people in this bucket here. Once you actually take a small proportion from here and almost everyone from here, ultimately the amount of people that end up in the testing positive bucket ends up very large, right? So the only way you can control this is by trying to get that false positive and that false negative down a lot. Now the false negative actually, ironically, from a purely getting positive tests problem doesn't really matter here, because we've kind of captured most of them anyway, and the numbers are very small. However, as you can imagine, from a medical point of view, false negatives are very bad, as we've seen in Ireland with, the cervical smear problems, because people are slipping through the net, they're not being treated, and as a result, by the time it gets identified later on, it becomes a big problem. But from a purely, is the positive test a true reflection of the underlying infection, it's not that big a deal. Like, there's a different thing going on. I'm not saying it's not important, but there's a different thing going on there as to, like, how many false negatives are we willing to tolerate, especially if it means that we have an awful lot of false positives, if there is that trade-off between the two. Okay? Now, at this point, I do appreciate, for most people, you're probably going on, that's all very well and good, Mick, but what the hell does this have to do with Bayesian statistics? Well, the reason why I always want to teach this is because conditional probability is confusing, and all of Bayesian statistics, and actually, to be fair, all of statistical inference is realistically is this problem writ large? So I kind of want to cover this reasonably comprehensively, just to give people a grounding on the way we're actually thinking about this. And this is like a really simple mechanism for trying to understand that process, because ultimately what we're doing is a much more sophisticated and complex version of this very simple calculation. Like in a second, we're going to create a calculation that essentially solves this analytically, so we don't have to worry about our simulations. But it's nice and simple I always like doing things with simulation if I can, for a couple of reasons. The first one is it's very, very easy to add wrinkles to your simulation. Like changing your distribution is like just changing a single line of code. Oh, I've got a continuous value. I don't want to use log normal anymore. I'm going to use gamma, or I'm going to use a log normal Pareto, or I'm going to do this, or I'm going to do that. It's generally very, very easy to do that with simulate, or at least relatively straightforward to do that in simulation. Whereas when you try to solve these things analytically, it can become an absolute nightmare. Also, and I guess this is a personal thing going on my preferences, is I always used to mess up the algebra, and I don't really trust my algebra skills anymore because I haven't really done it properly in 20 years. And I always used to mess that up, whereas I found it much easier to find errors in my code. But then I realized very quickly, so that was, at the start, I just used to feel guilty and lazy that I just didn't want to do the maths. But once I got older and I realized, actually, no, once I've actually written these things in code, it's much, much easier for me to start throwing on wobbly bits and adding on weird edge cases and sticking this thing in the side and just essentially getting a more sophisticated model that the mathematics and the analytics just can't keep up with. So that's basically what we're trying to do. We're just kind of creating these simulations, but ultimately we're going to do this, but in a much more sophisticated way, where we don't actually have to worry about how it's working to a certain extent. We can kind of let the cleverer people do all that work for us, and we just have to focus on getting the inputs right and getting the outputs right. But basically what we've built here is a really, really simple Bayesian inference engine, right? Probability of the underlying prior probability for someone having an infection is 1%. And now that we've conditioned on them taking the test, we know that the probability, not the likelihood, the probability of them actually having the virus is now 16%. So in some ways, like if you think of it in terms of like lift or whatever, it's very successfully like there is a strong signal in getting a positive test. It's just not nearly as strong as you would think it is, given the input numbers you're expecting. Because we're talking about like 95% accuracy here, but somehow because of this low prevalence, it's suddenly now only 16%. And if we were go for a lower prevalence, like, you know, this is 1 in 100, let's say it was 1 in 1,000 or 1 in 10,000 or 1 in a million, that number gets much, much lower and relatively quickly, just because of the way the stats work. Okay, I'm very conscious I'm been talking a lot. Does anyone have any questions about anything I've said there? And like I said, I didn't really want to go into the simulation too much because I'm trying to keep it relatively code neutral. But anyone, like, this is basically a programming exercise. You know, you simulate 2 cohorts of the population. One of the cohorts is infected, one isn't. You base it on the input probability. Then given, you split them into the 2 and you do the results of the test based on whether or not they're infected according to your input probabilities, which is your 5% or your 95%, whichever way you want to look at it. You end up with a big table of data, and then you just filter down on the positive tests and what's the proportion of positive tests that actually are infected. And you get a result of about 16%, about 1 in 6. Okay? Okay. So we can actually do this analytically for the purposes of this, because the reason I wanted to do this analytically, normally I wouldn't do this, just because but for this, it's so simple to do, and it's much faster rather than running a whole load of simulations and getting outputs. And we can calculate exact answers rather than, you know, estimates based on simulation and having to run a whole load of simulations to get, you know, decent accuracy on that. So what we're going to do is basically calculate it out. And essentially we've got this, I'm not going to go through it the whole way, but essentially it just boils down to this simple formula. And we find that given these input values of a 1% underlying prevalence, 5% false positive, 5% false negative, we get that, again, our simulation was actually quite accurate, but we would kind of expect that. We had like 10 million patients, right? So we would expect for that level of sample size, we would expect our underlying proportions to be relatively good. But again, as those numbers get smaller and smaller, that estimate gets more noisy because you have a lot less numbers going in. It's just like, you know, it's a low, because you just don't have a lot of data on the infected people when you have a very low prevalence. So you have to end up with unfeasibly large numbers, whereas the maths just kind of works out. So what I'd like to look at is, I'm going to skip all this, but it's a quick thing we've done with the function is, you know, what does the effect, what's the posterior probability of being infected as a function of the prevalence? So as the prevalence in the population gets bigger and bigger and bigger, you can see that our test, a positive test, is more and more indicative of actually being infected. So the higher our population prevalence goes, the more and more accurate. And what's happening there is basically, if we think of it in terms of 2 buckets, basically these 2 buckets are now getting closer in size. So the small proportion coming out of here is now getting is now becoming less and less relevant compared to almost all of these coming down, right? So that's kind of the intuitive feel behind it. But what we can see is that a positive test being true doesn't really have much of an effect. So if FPR there is, this FPR value is a false positive rate. Whereas if we look at a false negative rate, as we get the false negative rate lower and lower, we see that, you know, even, okay, initially a very low prevalence still has a problem, but once we get really, really low false negatives, the positive test becomes more and more accurate, right? And again, that makes more sense because basically, again, if we can think of it, and I'm going to keep using this example, is, so this is our infected population, and this is our uninfected population, and this is much, much bigger than this. If we can get a very, very small proportion of people coming out of here, and almost all of these coming out, which is kind of the way we're set up. Well, then once you're down here, there's going to be a lot more people coming from the positive than the infected bucket than people coming from the uninfected bucket. So our conditional probability is going to be much higher. That's kind of where we're coming from in that. Okay, and I get it. It kind of, and just this was more, again, like I said, I run these workshops because it helps me to think about stuff, and I was just curious to think about how that works. So what I created was a couple of heat maps of the posterior probability. Again, like I said, this is the probability of a person having gotten a positive test to actually be infected. Considered now, again, these are all just basic statistics. I want to reiterate this for all my YouTube viewers out there who think I'm suddenly making political statements about COVID. This is purely a statistical thing that the real world has to deal with to get around these problems. And it's why you find, like I said, again, why you have, when you have rare events, it's why they're very hard to detect statistically, because you have this low base rate problem. And the problem is you just get swamped by false positives because your false negative rate, it's very, very, very hard to get a false negative rate down. So we can see, look, as the prevalence goes up, and this is just, so essentially this is, I've used a faceted here. I'm faceting by the underlying prevalence in the population. And then it's a two-way tiles of, here's the different false negative rates and different and equivalent false positive rates. And then we have a heat map basically going from 0 to 1 of what the posterior probability is. Okay. So you can see here as the prevalence gets higher, and the red is what we want because it means that essentially a positive test is highly indicative of an infection. We can see that as the prevalence goes up, it's actually less and less of an issue. But with a relatively low population, we essentially need high rate of false positives and a low rate of false negatives. Okay. So that's kind of where we start. And then for anyone who cares about the stuff, I always just dump out all our stuff in there. So that's basically I'm not going to go into a whole load more detail. If any of you were at my previous Bayesian workshops, I used to cover this in a lot more detail. I'm not going to bother here for this because it's not really why we're here, but it's a useful framing advice for that. But if we have any more questions about the stuff I was talking about, or noticed any mistakes, because it's very easy to get my naming wrong in this, please just hang around at the end. I know it's about 8:30. We'll go on for about another 20 minutes. But what I want to switch my attention to now is, essentially a real world example of how we use these kind of things in the real world, using Stan, using, Bayes' rule, or like the Bayesian reasoning, I should say, and where we're going to go. So essentially I'm not using a real world data set yet. I'm going to use them later. And the reason I'm not using a real world data set just yet is because I want to start going to a question from one of the speakers earlier about generative modeling. Is I wanted to create a synthetic data set first. And I wanted to do that for a couple of reasons. The first one was that in some cases, I've had issues fitting these models. And when I've had issues fitting these models, it often tells me, in my experience, it means that the model I'm trying to fit isn't explaining the data I'm trying to model very well. And those there's a thing that, again, Andrew Gelman has a thing called the folk theorem of statistical computing. And that is that computational issues tend to be statistical issues or model issues in disguise. And that has been my experience too. When I've had problems fitting models, it's usually because there isn't a good fit between the data I've observed and the model I'm trying to fit. And, when you're collecting with a real world data, your model is just a model of reality. It's not necessarily a good fit to what you're doing, and you don't know that in advance. Whereas what I can do is with generative modeling, I can create some synthetic data using known input parameters that I've created. And then I can try and fit my models to that synthetic data and check to see, can I recover the original parameters that I've built? Now, that sometimes sounds like circular logic. It's like, well, you know, what's the point in that? But actually, it's a really, really useful exercise because it's a very good way of identifying any potential problems that your model might have when trying to use it with the real world. And again, this goes to the difference of machine learning versus statistical inference, in that in some cases you just don't care, right? It doesn't really matter whether or not it's quote unquote a good fit. I'm going to have some various, I'm going to create my training and test split, and I'm going to train my model, and then I'm going to test it. And as long as my cross-validation is okay, I don't really care. However, it is really important when you're trying to quantify uncertainty, because what you want to do is to make sure that your inferences are valid, and that's important, because otherwise, if your inferences are not valid, then essentially the numbers you're getting are garbage, and you don't know if they're right or not. And for all intents and purposes, again, you don't know if the answer is a good one or a bad one, and you have no real way of finding out. So essentially, you can't trust it. But also, you want to make sure that when it's one thing making a prediction, it's a harder job to get a good estimate of the uncertainty around that prediction. So therefore, if you're not building your model on solid principles, then you can't really do solid inference based on them. So that's kind of why you have to kind of care about these things. So for that reason, where I'm starting is I'm just going to start with essentially a synthetic transactional data set. So if you think of it like an online retail, so we have a whole bunch of customers, they're transacting with a certain amount of frequency on the system. And what we're trying to do really simply is get a sense of how often a given customer transacts with our business. And we're starting in a very, very simple way. We're basically assuming all the customers transact around the start of the year, and then they keep transacting for the whole year, and then they stop. So we're just capturing, it's a really kind of made up system, because in the real world, it's much, much more complicated than that. But we're going to start with a very, very basic thing where we kind of have a uniform window of observation. And what we want to do is the number of observations within that year, and get a sense of what's the underlying transaction rate for that. Okay? Have I kind of explained? Now, this ties into the kind of the buy till you die models. If anyone's familiar with those or have heard about them, this is kind of one of the building blocks for that. And I've done that very deliberately. Basically, the buy till you die models have a similar approach, but they make a couple of additional assumptions. They basically assume that a customer transacts at a regular, with a single transaction rate over time, and they do it basically while they're still active on the system. And you basically build the model down into two parts: being active on the system and transacting on the system. And they combine the two, and there's a whole bunch of things that we're going to get to, and we will get to that later on. But for now, rather than adding a whole load of complicated stuff, I just want to keep it really, really nice and simple. So all we're trying to model is an underlying transaction rate. Now, each customer has their own transaction rate. We're not making the simplifying assumption that every customer has the same. What we're saying is basically every customer at creation has an underlying frequency that they transact at, and that they, over the space of the year, they are always going to transact at that frequency, and then they're going to stop. And then where we're going to go with this is we're going to start basically estimating that underlying frequency by saying how many transactions did we have over the year, and basically the transaction rate is going to be essentially the number of transactions divided by the observation window, like a year. And generally the way we've done it is we try to use units that are very natural. So the one I've chosen is weekly, because weekly seems to be a decent number. And also just on other data sets I've observed, and I guess this would probably depend on the business, but based on the data set we will use later on in the workshop series, about one transaction every 4 weeks, or 0.25 of a transaction rate, is kind of an overall average. So that's basically what we're going to work off. So we're going to work in, we could do monthly as a result, but I think you do get customers that transact more frequently than that. And weekly just seems to be a nice kind of way in which a lot of these models work. So that's the one I've gone with. But I mean, there is nothing, as far as I'm aware, the models would work pretty much equivalently if you went monthly. And some businesses, it might make more sense to work on a monthly basis rather than on a weekly basis, or maybe on a daily basis. Like if you were dealing with something like, you know, like Tesco or something, or where you're dealing with, you know, you're or like a paper shop or something like that, where people are coming in every single day and you're somehow trying to track all that. Okay. All right. So before I begin on this, does anyone have any questions? I'm very conscious that I'm doing all the talking here and I'm not getting a load of questions. So I just want to make sure I'm not talking absolutely over everyone's head. Oh, great, Steve. I see you've figured it out. The other way to do it, by the way, is you could just do a clone and then do a git checkout. All right. So we have some customers. I kind of, like I said, this is synthetic data. I've started with some really, really artificial data whereby it's a single year, and I've just got some cohort data, which is basically something, it's not particularly relevant for this. We're going to talk about it later. And then I have some simulation parameters. Most of these we can ignore. Again, it will become relevant later on in the workshop. But for now, the only thing we care about is I'm basically generating a whole load of lambdas. So the lambda is the underlying transaction rate. So what I'm doing with my generative model is I'm creating n customers. In this case, I've created 50,000. They all start transacting at the start of the year, but we don't really count that one because that's considered, and for reasons that we'll be talking about later when we talk about buy till you die. How would you answer? Hi, Ash, how you doing? I will talk about that at the end, if that's okay. We can talk about that a bit more. I don't necessarily have the answer, but I also don't want to distract myself from this right now. And I think the strong answer to this, if you need a quick answer right now, is my classic one, which is it depends. But we'll talk about that a little bit later. That's an interesting question, and I do want to address it. But just give me maybe 20 minutes, and we'll talk about it at the end. So, okay, so getting back to this. So we've generated our synthetic data. Basically, at some point on the first day of the year, in that 24-hour period, randomly, I've done it randomly, the person transacts, which essentially activates them on the system. And then they transact for the full year. And then, so we've observed basically from the 1st of January 2019 to the 31st of December 2019. So it's a 1-year observation, and they're going to transact throughout that, right? And each person up front, we're assigning them a lambda value using a probability distribution, okay? So they're getting some lambda value, which is essentially what's the average transaction rate per week. So it's a weekly transaction rate. So you can see here it's 0.6. So they get about 0.6 transactions a week. So that's what, about 2.5. So let's say 5 transactions every 2 months, okay? And again, we're going to assume a Poisson rate for this. We could go with like negative binomial and all these other kind of fancier models, but we're just going to start very, very simple. We assume that once a person has a transaction rate, it's a Poisson, okay? Now, just to ask before I do this, is everyone familiar with the Poisson distribution? Does anyone need me to explain that? Because I'm happy to do it, because it's quite important. And one thing I have, and it does drive me a bit crazy, is a lot of people make these very broad assumptions about, you know, the units of thing. Oh, please explain. Okay. So a Poisson distribution is basically, it's a distribution for count data or event data. So discrete events. And what a Poisson distribution does is it basically explains how often something will occur in a given time period, right? So if you think of it in terms of, it doesn't necessarily have to be time, but the easiest way to explain it is through time, but it could be anything where you have some kind of dimension of that you're recording along. So if you think of it as a manufacturing process, it could be how often in a meter of cable do we, or if you think of it as terms of cloth in a textile factory, it could be the number of missed stitches per meter, you know, because that would be more relevant than time, because depending on the different rates, what you really care about is the units. But so it doesn't have to be time. but it's the easiest way to explain it is time. So you have basically something that you're observing on an ongoing basis, and it's how often does an event occur. So if you think of it like a bus, you're standing at a bus stop, right? How often do you see a bus arrive, right? One way of modeling that is through a Poisson distribution, and it has a couple of very big benefits. So the key one with a Poisson distribution is that it's memoryless. So basically, with a Poisson distribution, let's say, for example, I see with a Poisson, and again, this is not real life, this is the statistical model. It's important to explain that. But with a let's say I have observed that a bus comes every 10 minutes. If the Poisson distribution was true, my average waiting time is always going to be 10 minutes, regardless of whether or not a bus has just arrived or not. So there's no memory. So there is no kind of clustering of events in a Poisson distribution. You might see it like through random, just through random processes. You will see events clustering together, but there's no underlying change in the probability. So that essentially your wait time is independent of how recently since you last saw it. So at any given point in time with a Poisson distribution, there is no memory. So let's say, for example, in a bus stop, if the Poisson distribution was true, if I'm waiting for and this actually, a lot of people would joke with Dublin Bus that maybe Dublin Bus is a lot more a Poisson process than people would argue, that if you're waiting 5 minutes for a bus, your average wait length is still going to be 10 minutes, even though you've been waiting for 5 minutes. So, and it's basic, and that's basic, and the Poisson, it's kind of the workhorse of these kind of discrete valued models where you get integer realizations. So essentially what happens is, if I have a Poisson distribution, when I have the underlying rate, I can kind of, that's all I need to know about the underlying probability distribution. It just has a single parameter, that rate. And that basically the variance is a function of the underlying mean. In fact, the variance is equal to the mean. So the standard deviation is actually the square root of the mean. So you kind of only have that single value. Unlike, say, a normal distribution where you have two parameters, you have a mean and you have a standard deviation, right? With a Poisson, you have a single value, which is a lambda. And basically, if you and just to show you, just to show it for people, essentially we get it. The values themselves are continuous. So if I create, hold on, and that's right, folks, I'm coding live. Hold on to your hats. So if I go lambda, say 0.1, I'm going to make 10 realizations. You can see basically most of them are 0, and about 1 in 10 of them will be 1. And actually, it's a bit more complicated than that because on average, you get 1 every 10, but you can get 20. You could get, some of them will be 2, some of them will be 3, and that overall brings the overall average up. Okay? So basically, that's what we're trying to say with this. We're basically saying, well, given that we have we've observed stuff. So because of course, in the real world, we actually don't know what the underlying lambda for a customer is. All we know about them is how often they transacted, right? So we have to start making some assumptions about it, okay? And that's basically what we want to know. And the reason why we want to know that is in customer lifetime value, in general, one of the important components of how valuable a customer is how often they transact with you. Or vice versa, this could evenly be a call center. This doesn't actually have to be, a transaction doesn't necessarily have to be a purchase or a sell. It could be how often they call tech support or IT support, right? So in that case, high frequency is bad. Whereas if it's a retail thing, high frequency is good. So basically for customer assessment and customer lifetime value, if you're doing like a very comprehensive analysis, you should also be accounting like the cost of administrating a customer as well. And you might have a separate model for how often a given customer like costs you money because they're constantly complaining or they're always having issues because they've got very complex requirements. And therefore, even if they're paying a lot of money, they're costing you relatively more money in maintaining them. And also returns. You could count your returns as a return process. So as a proportion, that would be probably your dimension then, rather than being time, your dimension would be per purchase made. What's the return rate? So there's all sorts of different ways in which we can model this. But again, In the real world, we don't have these underlying values. We just have data that kind of looks like this. We have this kind of transaction data set here. And actually, what I should have done was show you it. Now, this, for those of you who went to my previous workshop, this will probably look similar. And let me just bring that up. So it's customer transactions. So in the real world, of course, we don't get any of these fancy numbers that we would like. We just have a table of transactions, right? And let me just view that actually. Hold on, view. So we have a table like this. You know, we have a customer ID. We can ignore the cohorts, but we have basically when the customer transacted and how much they spent, okay? And actually in the data set that we used for the workshop last week, that's basically what we had. We had a couple of more fields, but we didn't have much more than that. We also had the basket, so we had some information on what they purchased. But for the purposes of this, we kind of ignore all that, at least for the first pass, and I don't think we'll get more sophisticated than that, certainly not in this workshop. You know, so all we really have information on is when they transacted. And later on, maybe we'll bring in their monetary spend as well. So from that data, we want to infer what the underlying customer transaction rate is, okay? Now, the very obvious way to do that is to just say, well, you know, we observed, say, 52 days in the year, right? And let's say we had 5 transactions. So the weekly rate is just 5 divided by 52. And that gives us an estimate for our lambda, right? And that's perfectly valid. There is nothing wrong with that. That is an estimate of the lambda, and that is what we would call the maximum likelihood estimate, okay? That's in statistics. You'll hear about people talk about MLE. Now, to go back to the question that we had from earlier from the person about the difference between the likelihood and the probability, right? That's where the likelihood comes in, because what you have is your Poisson distribution will have a likelihood basically of all the different values of lambda that it could possibly be. And if we observed 5 events in 52 weeks, right? The 5 over 52 value will be our maximum likelihood. It's the point that maximizes that likelihood curve for the data we've observed, okay? And that becomes like our point estimate, okay? And that's typically how statistics was always done, like basically, you know, fitting a model in like fitting a linear model or a GLM or all them essentially uses maximum likelihood techniques. So what they do is they take the data, they use a likelihood model, push the data through, and it creates a value. And then you set the parameter that maximizes the total likelihood of all of that. Or in some cases, it's the log likelihood. All right. So that's basically what they're trying to do. They're just optimizing that. And the value, the optimal value for all of them is the output of your statistical model. It's like your best fit value. Now, what Bayes does is slightly, yes, Marion, for this, yes, I won't get to it this week, but later on, we're going to be dealing with churn and all of that. But for the purposes of this, of keeping it simple, I'm just assuming no one dies within the 52 weeks. Okay, yes, that's a very important point, but I'm going to get to that later. Okay, so that's our maximum likelihood, right? And oh, sorry, just to point that out, it's that aspect that makes things like the Pareto negative binomial useful, because it's estimating both the lifetime and the transaction rate simultaneously. And that's where we're going to get to, okay? But for the purposes of this, I want to ignore that because it causes fitting issues and other things that we're going to talk about later. Okay, so that's basically where we are. So what we're trying to do is, though, we're going to do something slightly more complicated than that, because as you've seen there, right, let's just put it back and let's show there is one issue with a point estimate, and I just want to show it again with this, right? So we have 100 customers here, right, who all have the same underlying alpha lambda, right? Because we've generated 100 customers there, but you can see in some cases they've generated no transactions, and in other cases they've generated 1. So the problem you have is that for any given set of observed values of a customer, there's probably a range of lambda values that could reasonably explain the values we observed, the data we observed. And that's what Bayesian statistics is trying to do. rather than come up with these point estimates and saying, okay, we're just going to go with the MLE and this is our answer. What we do in Bayes is, because we can use integration and we can create posterior distributions, each customer will have a distribution of possible lambda values that might explain that, that reasonably explains these values. Because especially what you can have is like, well, just to show, right? For any given value, let's double the lambda, right? There's still lots of zeros in there. There's a few more twos, but given that all we can see is what we've observed, like a customer who's had 0 transactions versus another customer who's had 0 transactions, one could have a lambda of 0.2 and the other could have a lambda of 0.1. So one is actually twice as likely to transact as the other, right? So, and we've no way of distinguishing between them. But what that does tell you is that we probably should have a distribution of values that makes 0.1 and 0.2 not necessarily the same, but they should also reasonably be part of whatever inference we're going to make. So if we're going to draw inferences on these, we need to not just assess the maximum likelihood value, we also want to use any analysis that covers the different range of values of lambda that could reasonably explain the data we've observed, right? And the problem is, like I said, we're not omniscient, right? We don't know what those values are. We can only go on the data that we've observed. So basically what Bayesian statistics is going to try to do is, in the posterior distributions, thank you, Nathan, we want to be able to capture that. So what we're going to do is, and we don't have time now because it's pretty much 10 to 9. In the next set, what we're going to do is we're going to start using Stan and Bayesian statistics to try to tease that out. Okay? And that's basically where we're going to go. And now I've actually jumped ahead and I've used Stan there. What I might do is add some code in the next time and just do it analytically using like a gamma distribution or wherever and go where we were. I haven't quite figured that out yet, but that's basically what we're going to try and do. We're going to try and take our observations, use them to make posterior inferences for like what set of lambda values could reasonably explain the data we observed, and then show how you now get, in some cases, quite a wide range of values that could be reasonably explained by that. And that's basically where we're going to go. So that's all I want to cover for tonight. Thank you very much. Like I said, this is going to be a series of workshops. I didn't get into any of the nitty-gritty this week. I just wanted to keep it reasonably high level, kind of explain conditional probability, provide some motivation for this. Sure, by all means, drop me an email, Yash, because I'm not entirely sure where you're getting at. Maybe pop me a mail tomorrow, and we can either organize a call or have a conversation about it. So yeah, so that's where we're going to go. So I'm going to leave it there. If anyone has any questions, like I said, I've deliberately finished a little bit early. If people want to go straight away, that's fine. But by all means, if people have any questions, pop them in the chat or unmute yourself or whatever. Happy to address anything. I'm not exactly sure when, but it'll be probably middle of February sometime. Like I said, we're probably a few months out from having talks. So if we don't have a talks, I'm just going to run workshops, and I'm going to run. I don't know how long this will go. I don't think it'll last the whole year, but at the same time, my prior probabilities mean I can't necessarily rule it out either. It'll also depend on the feedback and how we're getting on and what we're doing with stuff. So yeah, if anyone's got any questions, by all means, ask them now, and then I'll stop the recording in a couple of minutes. Or if people would rather I ask this without being recorded, I'm happy to field them now. In fact, I will just stop recording now. Probably seems to make the most sense.